Alright, so today I want to go over some more interesting stuff. Now that we've covered all the postulates of quantum mechanics, I'm going to go deeper into this topic of quantum field theory. And so in order to start doing this, I'm going to go straight into the actual question. Why study this, right? So oftentimes we don't actually think of this in this picture where if you were to consider spectroscopy, for example, spectroscopy is a really good tool to actually help us visualize a lot of the complex stuff that happens in quantum mechanics. Because we take, for example, atomic spectroscopy. If we have a nucleus. All right, my pen is already not working. We have a nucleus. Suppose there's protons and electrons in this nucleus, and surrounding this nucleus is some electrons. All right, and I'll make the electrons a different color. Say we have electrons surrounding the nucleus here, like this. Okay. And I'm not going to bother doing the chemistry of this. In this case, if this was stable, this would be, I don't know, what's the atom with 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So I believe this is fluorine, right? If we want to do some spectroscopy on this fluorine, what we do is we shine some light. Right now, suppose we shine some, we're shining light at this sample. This is of a particular wavelength. All right, this happens to be this color, this wavelength. Remember, colors are associated with wavelength. And so this is our electron gun. Right, our electron has some specific frequency to it, or not electron, our photon gun. So we're shooting photons from this gun here. So this is the photon gun. Or our laser, if you will, /laser. That's this thing. And we're shining electrons, or photons. I keep on saying electrons. Yeah, it's been a long day. Photons are, we probe this atom with photons, and then we can get a scattered photon, perhaps at a different frequency, being detected. Okay. And so we have our detector. Say we have our detector right here. So this is our detector. So this is our detector. And we want to ask the question, what exactly goes on right in this region here? So this region is of particular interest. So let's take a look at how we might be able to model this situation where we have photon of specific frequency coming in, so our incident frequency, and then a photon of our final frequency, or our scattered frequency. These are two different states. Right, this is a state that's labeled with this frequency, and this is a state that's labeled with this frequency. Right. So how exactly can we model this? Well, we can use a Feynman diagram, right? If we have time, here's our Feynman diagram. Feynman's diagram. So I'll just Feynman's diagram. We have an electron. So we start off with an electron in this region of the molecule. So we have an electron. and a photon. So here's in time axis. So at the same at moments in time, at the same moment in time, we have an electron and a photon. Okay, and this is our photon right here. So this is our photon. This is our photon right. This is our outgoing photon. So photon incoming, photon final. So this is our photon incoming. And what happens is that this photon eventually comes in contact with this electron, right? Something happens that causes the photon to leave, right? And it bounces off the electron, for example, right? And so this here is our final photon, and these are different states. These are photons in different states. This could be an electron in different energy states, in a different energy state as well. So the energy of this electron, the energy, we could have an E1 state, and then right here we could have an E2 state. Right? So this is kind of putting the Feynman diagram into perspective, right? Because this is something we all know and love from general chemistry and from medical physics, medical imaging kind of stuff, where we really do heavily rely on what happens to our outcoming photons, right? Because that gives us that's what's going to give us information on what happens during this collision process, right? In words, we can say that this photon, so photon incoming, gets annihilated as it comes in. Annihilated, and photon final gets created. So we have two states, two photon states, one of which is incoming, and that gets annihilated, and one of which is outcoming, and that gets created, right? So this is our setup. I'm kind of using spectroscopy as an example here to motivate our interest in quantum field theory, because we want to know exactly what's going on in this picture, right? And I'll come back to other pictures that I've drawn later on, like the field picture of states, right? I have these states. This helps us sort of organize ideas on how Lagrangians work over state space, right? We're not going to deal with that, so we have right now, but like I said before, we have Lagrangians, we have Hamiltonians. We'll come back to this picture later, okay? But for now, I'm interested in this picture. This is a very simple picture that from physicists, biologists, chemists, we can all understand this picture, right? And so this video is going to be kind of long, but so don't have this the length of this video turn you off and want to go on to the next topic here, because we're going to lay some important groundwork on what creation and annihilation operators look like, right? So we're going to have creation and annihilation operators within this space, right? And these creation and annihilation operators. So our creation operators, that would be here associated with creating a particle, and annihilation operators are associated with annihilating a particle. And these operators exist everywhere in space. Just like we said, states exist everywhere in space. And these creation and annihilation operators are doing things to those states. So we're going to start off we're going to motivate this discussion of creation and annihilation operators by starting off from fairly simple principles. We're going to start off with the Schrodinger equation. So the Schrodinger equation looks a little something like this. I'll rewrite it. So h squared over 2m, and our operator dx squared. And we're particularly interested in our Schrodinger equation in which the potential is the potential for a harmonic oscillator. So m omega squared x squared. Right. So we have this operator. So this is our potential energy. Oh no, that's not our potential, that's our kinetic energy. So this is our kinetic energy. That's usually denoted with T. This is our potential energy. Right? T is a function of the derivatives of x, or the double derivatives of x. So this is a function of derivatives and double derivatives of space. And this is a function of space. Right? And this is operating on some wave function. And this equals our energy eigenvalue times our wave function again. This is our famous Schrodinger equation. All right. And I sort of wrote this mu term in a way such that if we set x equal to the square root of h bar times m w, and then there's a q right here. So I set, if I were to set x to equal this, then what we can get is another, what we end up getting is this. We could plug this in. We could plug this. Go ahead and plug this in. What we get is h bar. Actually, before we plug this in, I actually want to talk about this really quick. I want to talk about why. Why are we doing this Schrodinger? This is the Schrodinger harmonic oscillator. This is the Schrodinger harmonic oscillator, right? Not just the Schrodinger equation. Remember, the Schrodinger equation is just an arbitrary mu of x. We're specifying now that this is a harmonic oscillator because we want to know what are these photons. Right? These photons, they are oscillating, right? They have a frequency. And they have wavelength, they have amplitude. So this is the potential energy for a harmonic oscillator. This is why that's interesting to us. We want to be able to apply an oscillating potential. Right? That's the rigid motion of electrons. So this can model the rigid motion of electrons as they sort of bounce back and forth as they try to stay in one place. But it can also model photons and their wave-like properties, right? And so, okay, so what am I going to do? I am going to replace this for x, right? And what I get is h bar squared over 2m times d squared, and then this is going to be d by all of this. So this is a reparameterization with these constants out in front. So we have h squared over m, or not 2m, oops, over mw. So that's going to be mw q. That squared plus our potential part. That's going to be 1/2 m w squared and then I'm going to have my pen's bugging out again. Going to have an h bar and then an mw and Q, then I'm going to square all that. All right, so this is our operator now. So I've literally just put in this for x, right? And then we're going to be operating our wave function that equals this. Okay, and so from here we can do some more simplifications. Remember, this is this right here. This is a reparameterization. We're really just reparameterizing our Schrodinger harmonic oscillator, right? And so when we do that, we're going to get this. Okay, so it's going to look like this, and so I put some stuff in here already for the interest of time. And what we have now is basically I'm taking constants out and I'm manipulating this equation. This is all just algebra I'm doing inside of this operator right here. And so I'm able to cancel out a couple of things, and we end up, you can go ahead and pause the video at this point, but we end up with this equation right here. Okay, so merely just by considering the harmonic potential, the harmonic form of the potential, or a form of the potential that models a harmonic oscillator. That's maybe a better way of saying it. This is the potential that models that it represents the harmonic oscillator placed into our Hamiltonian. Because remember, our Hamiltonian typically is just our kinetic term plus our potential term. And usually in quantum mechanics, the potential term is an arbitrary term. What we put into the potential term is going to help us define exactly what kind of system we're dealing with. And we're dealing with oscillatory systems, right? We're dealing with electrons moving back and forth. That's an oscillatory motion. We are also dealing with photons that behave like little oscillators, right? And so by placing this form of the potential into our Schrodinger equation, we arrive at this right here. Okay, so I've rewritten that on a different slide here because we're gonna go deeper into this, and by deeper I mean zoom up on this guy right here. So zoom up a little bit more actually. Maybe one more. That's good. So this is our operator. So this is our Schrodinger equation. Remember, this is our Schrodinger equation, but this is assuming we are modeling oscillatory behavior, right? This is the equation. If we assume that we're modeling oscillatory behavior, all right? Now, and Q, if we remember, Q was, so if we remember, we made this reparameterization where x is equal to the square root of, if I remember correctly, yep, it's going to be mw, the mass, times the frequency, rotational frequency, times q. So this is our relationship between q and x. This is our reparameterization that gave us this equation. And so what can we do with this now? So if let's probe this a little bit deeper. We can actually, let's consider, for example, let's consider this right here. So we're going to consider dq plus q, and then have that be positive, dq plus q. And then we want to do plus dq q minus q dq like this. Right. So what exactly is this right here? So this is equal to, well, all of this is going to be this, right? Because I'll do I could FOIL this out. This times this, which is going to give me, actually I want this to be negative because we came up with a negative down here, I believe. Yeah, there's a negative right there. So yeah, that's what threw me off for a second. Okay, so this right here is all this, but this, why am I adding this term? Well, I'm adding this term because what we'll find here, actually, is that this is going to be just this part right here. This is equal to 1. And let's actually investigate why this is equal to 1. All right, so this is equal to 1 because if we apply this to just any old function, all right, so let's say dq times q times f of q, and then q dq times f of q. We apply this to this is some arbitrary function f. We're just applying this part right here. What we're going to get is that this here, we do the chain rule on this guy because this is the derivative of two things that are a function of q. So this right here is going to be dq of q times f of q plus q dq, and then we're going to put an f of q right here, and then minus q, this whole part right here, dq f of q. Okay, well, these two guys are going to cancel out. Right? We have, because one's a negative, one's a positive, so these two guys are going to cancel out. And then this here, well, ddq of just q, that's going to be just 1. This is just, this right here is 1. So what we end up getting is that this right here, or this right here is equal to, this whole thing right here is equal to f of q. Okay, so we take the f of q's out, we can maybe think of dividing both sides of the equation by f of q. We get 1 on this side, right? So if we divide, I can rewrite this. We have dq q f of q minus q dq f of q, and then that equals f of q. So I just rewrote this right here. We can imagine dividing, I think I got the wrong pen out. Yeah, there's a pencil, but that doesn't matter. Okay, go back to a pen. We can think about dividing both sides of the equation. Now what we get is that dq q minus q times dq is, this is an operator, and it's equal to 1. Right? Because if we divide both sides by f of q, we get a 1. Right? And so we have that, let me see here, that this, all of this right here is equal to 1. Okay. So I will come back. And so why do I do this? Because when we do the FOIL, when we FOIL this out, this is actually, these are those two terms, this times this, and then that'd be this times this, and this times that. right? This right here is this, and this right here is this. So what we end up getting is that h omega over 2. Actually, I'll forget about the constants for a second. What we get is that all of this right here, so d dq plus q squared is equal to this right here, so dq plus q times d dq plus q, and then plus 1, because this came from those two inner terms, those two inner FOIL terms. And so that's all. So now here's the big quantum jump here, if you will. This is going to be, so if we put this in for our Schrodinger equation, so instead of this, which I'll do right here, so here's our Schrodinger equation. So what I'm going to have here is h bar omega over 2 times all of this, so d dq plus q d dq plus q plus 1. So I'm putting all this in for this right here, because this is what was here originally. And then we have the rest of our Schrodinger equation, which is this right here. Okay. So from here, this is, okay, so this is where I say we're going to, the quantum jump is, I'm going to call this a dagger, and I'm going to call this a. And what are these? Okay, what we're going to find out, and this video again is going to be kind of long just to explain exactly what these are and to go in depth on these guys. These are creation and annihilation operators. So this is our creation operator. Creation and annihilation. These are our creation and annihilation operators. And these are going to be extremely important in our study of quantum field theory and quantum physics. Okay. These are super, super important objects. And I can't really stress how important they are, other than to make an hour-long video on this probably. But let's probe these guys a little bit more now, because what we're going to be interested in is how these things are related to the Hamiltonian. Okay, so let's start off just by reminding ourselves that this right here, this is the Schrodinger equation. We can rewrite this now. The Schrodinger equation, the Schrodinger harmonic oscillator equation, has become h omega over 2 times a dagger a. And actually, before I do that, I missed a little something here. We can take this 2 right here and put it in here. Put a 1 over square root of 2 right there, and a 1 over square root of 2 right there. right? Because these are just constant. We can bring them out, and we get 1 over 2 back, and these guys are included in our operators, in our creation and annihilation operators. So, so what does this become? Right, this becomes, and then this actually has to be, if we're going to take a 1/2 out, that has to be a 2 right there. All right, so this, okay, so now we can rewrite the Schrodinger equation. This is h bar omega times, let's see, so times a dagger times a, so a dagger times a plus 1/2 psi q, and then that equals E psi q. So this right here, this is our Schrodinger equation, because all we did was we reparameterized, right? We simplified, and we got down to this equation. And this equation is the same thing as this equation. We're just identifying, we're just sort of defining our creation and annihilation operators now. But hidden within this equation, again, this is, I'll write it down for very clear purposes. This is a Schrodinger, Schrodinger. This is our Schrodinger harmonic oscillator. I don't know if I spelled oscillator right, but this is our Schrodinger harmonic oscillator. And so what can we do with this now? And so what I'm going to do now is we're going to start defining a bunch of stuff. We're going to start defining what are these Q's, right? What are these Q's? Okay, that's the first thing we're going to do. And then we're going to explicitly write out other forms of A and A dagger. And then from there, we're going to see exactly what these things, how these things are actually really, really helpful in determining quantum states of our system, or quantum states of our harmonic oscillating system. And so yeah, let's begin that process now. Okay, so before I actually get into those details, though, I want to talk about, just really briefly, what we've done again so far, because I don't want to shy away from repeating myself. So if I come back up here to this was the Schrodinger equation, right? This was the Schrodinger equation after that reparameterization that we did up here, right here, right? So this was the reparameterization. We said that Q is a proxy for this spatial variable x, right? And we just put all these constants out in front of it. And by doing that, we arrived at this equation right here. And then from this equation, we've managed to place creation and annihilation operators in it just by rewriting this a little bit. But this right here is an important equation. This is the Helmholtz. This right here is what's called the Helmholtz equation, or the Helmholtz H-O-L-T-Z, I think. This is the Helmholtz differential equation. So diff EQ. And this is a very, very important differential equation. This is the equation that describes, as we've seen, a wave-like structure. Because remember, this is the wave potential. This is the wave potential that we've started with, and we've arrived at this Helmholtz differential equation, and then from the Helmholtz differential equation, we've arrived at this other form of the Schrodinger equation with creation and annihilation operators in it. So now I want to talk about canonical variables, right? So I'll rewrite here, right here. Let's see, we reparameterized this to say that x was equal, our reparameterization was h bar over m omega q. This really is just like I've said, a reparameterization of x. We just put this constant right in front of q, and we have x. What q is, it really, if we just think about it in its most simplest form, q is a proxy for x, right? This is all some constant. This right here is all some constant, right? The square root, also, I could say that the square root of m omega is equal to c. I'll call that c. And so in this case, x is equal to c times q. This is, and c is just a constant. That's a constant. It's a very small constant. And this is what we can kind of think of this as quantizing, because the square root of Planck's constant. Planck's constant already is super small. We take the square root of that. This is really small. So we could think of x, this position variable, is shrunk down by this constant, and we define the new variable as q. Right. So I'll get rid of those. And if we can now define p, let's define p as the differential with respect to q, right? So, and this is important. Actually, we'll call that the negative differential. Actually, let's put an I right here, because this is going to be important. If we define this p as di dq, what we've done is we've taken this this is a spatial coordinate q, and we find the derivative of some we can take the derivative of some arbitrary function with this respect to this canonical, what we call this a canonical variable, right? And what we get is a canonical momentum, right? So q, I'll say q is canonical spatial coordinate. So I think there's a T to make that, because the C makes it special, I think. Spatial coordinate. It's canonical in the sense that it encompasses all of the possible positions, right? The Q is, again, just a proxy for position. P, on the other hand, is canonical momenta. So our canonical momenta with respect to all the possible spatial coordinates, right? And momenta, again, it's the change, and it's the change with respect to the spatial coordinates. That's why we call this the derivative with respect to q. If we define p in this way, then A and A dagger, so we'll say A is therefore equal to what we said over here, these guys. These right here, they just become P, right? I times P. Right? So what we end up getting is that A is equal to 1 over the square root of 2. We have the square root of 2 there. And we have Q plus IP. So Q plus IP P, right? Because we bring, we bring this over. When we bring it over, we make it positive, and we have this right here. Similarly, a dagger is 1 over square root 2 times Q minus I P. Okay, and so our creation operator has become is now in terms of our canonical momenta, just by making this definition. But you might think, okay, that's all fine and good, but what is the benefit? What exactly is the benefit in doing this? Well, before we get any deeper into this concept, let's consider Q, P, and we want to consider this right here. This is another really important object I think I've touched upon in previous discussions. This is the commutator between P and Q. So we want to know what the commutator is between our canonical positions and our canonical momenta, right? And this is, let's see here. So what is this? So this is going to be Q P minus PQ. This is how this is defined. And this is going to be equal if we put this in terms of, if we take P and we put it in terms of Q, what we get is, so Q is going to be, let's see here, so this is going to be the P, so this is going to be negative Q I D dQ, and then minus negative I dQ like this. This is this is what it is just in terms of Q. And we could take a negative I out. If we take a negative I out of this, what we get is, let's see here, this is going to be, let's see, this is going to be Q dQ, and then minus, actually I think I'm going to take that minus out. This is going to be, so if we take the minus out, this is going to be a plus, and then we're going to have dQ, Q, right? Let's see if is that right? So that's going to be, we take a negative out of there, and what we get, this is going to be negative right here. Okay, so if that's a negative, then that means this is going to be, we can rearrange this, dQ, Q minus Q dQ. Okay. And then this becomes 1. Or this right here we said before was 1, and we get I. So Q P is equal to I. I'm going to check really quick. So we brought the I out. That's going to make that negative. We bring an I out of here. It's going to be positive because minus. All right, that should be good. All right, this right here is an important relationship. This right here is the commutator between our canonical positions and our canonical momenta variables. right? And what we find here is that they're related to each other by I. Okay, so this is going to be an important relationship later on when we make some other derivations. And so we can review. Let's review again, because I'm not going to shy away from repeating myself. We went from Schrodinger to Helmholtz by doing this reparametrization. We went from Schrodinger to Helmholtz by doing that. Then we went from Helmholtz to a different form of our Schrodinger equation by merely taking a look at this Helmholtz merely taking a look at this Helmholtz differential equation and rewriting it. Right. So I'll just write right here. So we went from Schrodinger to Helmholtz. Okay. This was the process of reparameterizing our Schrodinger equation, in which the potential energy modeled that of an oscillating object. And then from Helmholtz, we made a little bit of a realization, and we got into this right here. So a dagger A plus 1/2, this differential equation right here. Okay, so that's what we've done so far. Now what I want to do is I want to sort of put this aside for a second, because when we make this, when we come to this point, and we start defining new variables, P and Q, A dagger and A, it becomes in our best interest to understand exactly what commutators are. So we have to step back a little bit now and understand exactly what a commutator is. So a commutator is let's start to understand exactly what a commutator is. Okay, so a commutator, if I'm going to put this in the most simplest terms, so we just finished talking about this right here, this process of Schrodinger to Helmholtz to this oscillating potential with creation and annihilation operators in them. I'm going to diverge a little bit, and I want to talk about commutators now, because commutators are super, super important in quantum field theory and QED and upper division physics. A commutator is more mathematical than physical in a sense, because how we define this is if we suppose we have two real numbers. So real numbers, right? Say we have two real numbers, A and B. Our commutator of A and B is actually going to be 0, because this is A times B minus B times A. And this is 0 because A times B, this is a real number that's the same as this. These two guys are equal to one another. Right, so this commutator really sort of defines not just a relationship between A and B, but it defines sort of the dynamics, if you will, or it defines what if you're dealing with real numbers, if you're dealing with if you're dealing with real numbers, if you're dealing with complex numbers, or anything like that. So in a sense, a commutator defines the algebra of two objects. Most generally speaking, an algebra. So suppose we have, so if we suppose we had like two matrices, right? So matrices, these things might be 3x3s, right? They have 3, and therefore they have 9 elements in them, 9 components. Same here. Here's another matrix. It's a 3x3. The commutator between so these guys aren't real numbers. These things are matrices. So maybe we can say something like this. right? So, and this is these elements. These are elements inside of this matrix space, if you will, right? Just like these are objects inside of the space of real numbers, or the domain of real numbers, right? And oftentimes, what we find is that the commutator for this matrix space of two elements, A and B. So actually, let's call this big A. Let's call this big B. And these exist in this sort of matrix space, and these guys exist in this real space. And so these guys here, they define, so if we have A and B, and we take the commutator of both of them, this is actually not going to be 0 in most cases. Because A times B is actually different than B times A, if we're dealing with matrices very frequently. And so the commutator defines, defines the space. It's a mathematical definition of what kind of objects we're dealing with, right? And all of the objects, and it's a definition that exists for all of the objects within this domain, right? So when we say commutator of two elements, A and B, forgetting now that this defines whether or not we are working with reals, with a class of matrices, with complex numbers, with quaternions, and so on, and octonions. And then there's different subgroups of these objects. Octonions, I believe, looks like that. It's an O. This actually defines. This is a very useful thing. And so if we were to consider, for example, an object, a dagger, and A, right? This is our commutator, or not? This is our commutator of our creation and our annihilation operators. And so what elements are these here? And what we'll find, I'm actually going to do the calculation here. What we're going to find is that these make up a very interesting subclass of, this makes up a very interesting domain. This is going to be equal to 1, right? And we could call this, we can call this the definition for our domain. So this is our, say, I don't know, call it our A. I don't know. I'm trying to figure out how we can name this. I'm just giving this an arbitrary name. A large lowercase a that looks like that. Maybe this is our creation and annihilation space, right? Or our creation and annihilation operators. This is, again, this here is going to define the domain of objects. It defines what type of objects we're looking at. Okay, so let's actually calculate this. So we now know what these things are. We can now calculate this. If we say that this is 1 over the square root of 2 times Q plus IP, and then 1 over the square root of 2. This is it's going to be Q minus IP. And then we want to do minus this guy, so 1 over square root of 2, Q minus IP, and 1 over square root of 2, Q plus IP. Okay. And so what we're going to get is 1 over 2. We're going to have a q squared out front here, minus I qp, so qp. And then remember, I is just a constant, plus I pq, and then minus I squared p squared. And then on this side, we're going to have 1 over 2 times q squared plus I qp minus I pq minus I squared p squared. Right, and so we can see here that we have some things starting to cancel out with one another. We have, for example, this is going to cancel out with this. This is going to cancel out with this. And let's see here. What we end up getting is, let's see, this is going to be 1/2 negative IQP plus IPQ minus 1/2 IQP minus IPQ, like that. All right. And then from here, we can actually see that this is, let's see here. So this is going to be 1/2, let's see. So if I bring, this is going to be minus IQP, and then here's another IQP. So this is going to be minus IQP. Keeping in consideration this subtraction sign right here. Then we're going to do plus this guy right here, IPQ, and then plus, because this minus and that minus, it's going to make that IPQ. And then this is actually, so this is going to be 1/2 of negative 2 IQP plus 2 IPQ. And what we're seeing here is that this is going to be, let's see here, we get, these two guys will cancel like that, and we get ultimately, let's see here, this is going to be IQP plus, that guy's going to cancel 2, IPQ, and then we see that this is I times the commutator of Q with P, and this is equal to 1, right, because this was I. And was that I or negative I? I can't remember now. I think that was I. That was I. Okay, and so that's going to be negative 1. But the negative, again, or negative 1, not negative I. But the negative 1, again, that's really all subjective. That depends on how we choose, where is it? How we choose this guy to be defined, our canonical momentum. If we don't have a plus here, which sometimes some papers won't, or some people won't put this minus sign here, then we're just going to have to flip signs around. But what we get now, so we have our our Q's and P's, their algebra looks like this. So our Q's and our P's, their algebra looks like this. I and our A daggers and our A's, their algebra looks like this, right? So we have this sort of complex algebra going on here, and we have a real algebra right here. Okay, I'm realizing now that this video is getting kind of long, so maybe in the next video we'll go over how these guys are related to our Hamiltonian. Right, and we're going to find that our Hamiltonian forms an algebra with our A daggers, and it forms an algebra also with our annihilation operators. Right, so these things, when we put Hamiltonians within the domain of our creation annihilation operators, we ultimately get commutators that look like this. So this guy is going to be omega alpha plus, and this one is going to be negative omega alpha minus, or not a minus, just A. Okay, and we'll see that these guys are related this way, and this is why we're going to call these guys raising and lowering operators, because this is a positive sign and this is a negative sign. And we have this increase by a factor of h bar omega and a decrease by a factor of h bar omega when we apply A plus or A dagger to our Hamiltonian, right? We get an increase. We get an increase here in our quanta. All right, and so with that, I will see you guys in the next one.